Okay, so this lecture should be kind of fun, and the subject is what's called dithering and halftoning. And the basic question we're going to answer today is, how do you print a grayscale image? Easy, you just send it to the printer, right? But in fact, printers don't deposit shades of gray onto a piece of paper. All they can do is take the black ink from your ink cartridge and produce splotches of ink on a piece of paper. And so if you're used to kind of like old-timey newspapers, you've probably seen pictures that look like this, right? This is the way that a newspaper renders a grayscale photograph as a series of different sized black dots. I've got small, less dense dots in lighter areas, and I've got, mostly black ink with some empty white dots in dark areas, right? And even though this may seem like, no one reads newspapers anymore, that's probably true, but, this is the way that printers and books work. So here's a picture of the refrigerator I just bought, and so here I'm going to try to put a magnifying glass up to it, and you can see that as you zoom in on it, the printer is in fact doing the very same, kind of dot pattern idea that the old-timey newspaper was. And here's another example. This is an example from my textbook, right? So I have a bunch of grayscale figures in it, and if I put my magnifying glass in and zoom in, I can see the same kind of dot pattern, right? So this technology is still important and relevant for any kind of rendering of an image on a piece of paper, okay? And so the question we're going to answer today is, what is the right way to turn a grayscale image into, we must turn it into spots of black ink. And the idea is that when we get sufficient distance away from the piece of paper, it looks like grayscale, right? So we might already have some of the tools to answer this question. Why don't we just threshold the image? Right, that's the easiest way to make an image into black and white, is just to say, show me all the pixels of the image that are below or above a certain threshold, turn those into white. And so let's see what happens when we do that. So I have a couple images in Matlab. So here's the image I'm going to be using kind of throughout this lecture. So here's a picture that has definitely got a bunch of shades of gray in it. And so what I could do is I could simply threshold this image and see what I get. Turn the warnings off. So let's say that since this is an 8-bit image, I just threshold it at the middle value, 128. Well, I can see that that actually produces a pretty crummy looking image. So here's my original image, and here's my thresholded image, which I can see is not really at all what I want, right? So, I've got this kind of weird, crappy texture in the bricks. The guy doesn't look very good. This text that used to be here is now unreadable. And so, this is not very appealing, and really no threshold that I choose will produce a very satisfying image. And in fact, this is kind of like a very extreme version of what we talked about early on, which is called false contouring, right? So if I use too few quantization levels, I end up seeing very obvious, banding in the image. And in this case, the banding is extreme, right? Because I only see, instead of getting a nice steady gradient of black to white along this shaded curved region, at some point it's all black and then it switches over to all white, right? So this is the same kind of phenomenon that you get if you try to quantize an image of the sky, for example, with only a few quantization levels. You'd start to see this banding. So look back at our quantization lecture earlier in the class for this. Okay, so thresholding is not the answer. So what can we do instead? So let's just say, looks terrible. And kind of, this is kind of the reason for this is kind of like what you call false contouring. So what can we do instead? Sorry, I realized I was doing this without actually having any notes in front of me. So the first idea is called dithering. Okay, so concept of dithering is very simple. All we want to do is add some random noise to the image before quantizing it. And so kind of the idea is, as a kind of a block diagram, take my original image and I add to it some uniform noise, some uniform random variable distributed between minus A and plus A. We'll talk about how to choose A in a couple seconds. And then I send that through a quantizer. And, you know, in terms of, if I'm talking about getting a binary image, then this could be just a threshold. That would be like a 1-bit quantizer. But in general, the stuff I'm going to talk about in this lecture can be applied to any situation where I want to do basically lowering the number of quantization levels. So if I wanted to make an 8-bit image into a 2-bit image or a 4-bit image, I can apply the same ideas that I'm going to talk about right now. And so I'm going to focus on the 1-bit image case here, but you know, you can apply this not just to images, but to general signals. And so the idea is that this approach of adding a little bit of noise is going to push some of the gray levels above the threshold of the quantizer and push some below the level of the quantizer, because this uniform noise is both positive and negative. And so the idea is it will break up some of those kind of false contouring regions. And so let me just show you a Matlab function that I wrote to do this. So I called it uniform dither. So it's pretty simple. If I don't supply any threshold, I threshold at 128. And otherwise, I just take a noise image that's the same size as the original image, I center it, I multiply it by some amplitude, I add to the image, and then I threshold it, right? So very straightforward. And so what do I get if I apply that to my original image? Well, here's my dithered image. I guess I call it uniform dither of the image. And I need to supply a noise amplitude. And so in this case, I'm going to choose an amplitude of 64. Let's see what we get with that. So let me close my images. So here, this image, it's not great, but it looks better, right? So kind of what happened was that instead of, for example, having all this region be black and all this region be white, instead, some of the pixels that used to be just below 128, because I added the noise to it, got pushed over to be above 128, and that's what these white pixels that are in this kind of region are. And so in theory, pixels that are close to the threshold, in fact, this grayscale level is probably pretty close to 128. If I zoom in on it, this is probably about half white pixels and half black pixels, and the randomness, is such that I don't really see any patterns in the noise. The downside is that this still looks like a pretty crappy image, right? So I mean, in white regions, right? Before I go on to say why it's crappy, the idea is that in the black regions here, where things are really dark, if I'm only adding up to 64 gray levels of noise, I'll never get above 128, right? So regions that were always going to be dark stay dark. Regions that are always going to be light stay light. Regions that are close to 128 plus or minus 64 in this example have the potential of getting flipped. And so this is better than pure thresholding, but still not great. And I can see what happens if I were to try, if I were to try a little bit higher of a threshold or a higher of a noise amplitude, then I start to run the risk of losing the image structure, right? So here, even pixels that were dark before now have the probability of being flipped to white. And what it looks like is just I've kind of put a noisy screen over the whole image, right? Kind of conversely, if I don't use enough noise, like if I just used 16, then I get back to something that is still looking kind of like a crummy, I get a little bit more detail in places that are right on the boundary, right on the 128 boundary, but most of the image still looks pretty bad. And so clearly this does something, but it's not what my newspaper or my printing press is really doing. Okay, so what we want to do is something a little bit different than that. And so this is, let me just say a note that this A should be on the order of the least significant bit of the quantizer to avoid kind of changing what I would call like the image structure. So in my case, for example, I knew I was going to threshold this at 128, and so I chose A to be 64. So I mean, maybe a good rule of thumb is half the half the level that I was to use. Okay, and as a a slightly more synthetic example, let's take a look at let's see. I guess I call this diag. So here's a simple grayscale ramp, right, from black in the lower left to white at the upper right. So if I were to just simply threshold that above 128, it would be just a triangle, right? And so that would be a pretty crappy version of making it grayscale. Instead, what I could do is I could dither it, and again, I'll use the same 64 threshold. Now what I should be able to see is, again, a little bit better. And here, actually, this kind of gives you a sense of that the dots get sparser as I get closer to the band. And in some sense, this line probably is, 192, which is 128 plus 64, and this line is probably 64, right? And I can see that if I were to change the value here, then I would get, a narrower band where things are varying. And if I pump it up, then I should see, something that approaches what looks like basically uniform noise, which is pretty bad. Okay, so what is a good alternative to dithering? Well, the next idea is called halftoning. And halftoning has kind of a history that involves things like analog printing and silk screening. So, here's the history. The idea is that I would take a projector, and through the projector, I would send the negative of the image. So if this is my original image, so maybe it has a black splotch here and a white splotch here, that would mean that things would be reversed over here in the negative of the image. Then I send that through a perforated screen. So the idea is that I have kind of a big silk screen. And inside the silk screen is a whole bunch of tiny dots. You can kind of think of these as like pinhole projections almost. And then I look at how the light passes through to the dots, and I have a big plate of photosensitive material. So this is like a photosensitive plate. And the amount of light that will hit the plate depends on how bright the source is over here. So for example, if I've got this white area here, then a lot of light is going to shine through the corresponding hole, and I'm going to develop the plate, with a fair amount of, I'm going to get kind of a big bright spot. I guess in some sense what I'm going to get are spots, because these are circular openings, so the only thing I can get are circular openings over here. So I'm going to get a bright spot over here, and I'm going to get, smaller spots over here that correspond to not much light coming through these pinholes. And then I develop this plate. And by developing the plate, I get kind of the inverse of my photographic material. And this kind of matches up with my intuition about how I should make dots that mimic the original image, right? So when I've got a dark area, I want to make really big black dots. And when I've got a light area, I want to make relatively small black dots, right? And so the idea is that, larger spots or larger dots correspond to darker, image pixels, course, this was all before the day of digital images, and so this is kind of, you know, the analog version of how you used to do it. So what's the digital version? So digital halftoning, again, it's a very simple idea. So what I do is I take my image and I divide it up into blocks. Excuse me. I'm getting over a cold, so my voice is a little croaky. So here's my original image. And I assume it's on the range of, you know, 0 to some amplitude, right? So in our case, usually A is 255. Then I add to this image a repeating what you call a halftone array or a halftone screen. And so this is repeating. And again, each of the blocks has the same range as the original image. So this image is made up of the same block tiled over and over again. And so on. Then I put this through a 1-bit quantizer that basically says return 1 if the result is above A and 0 otherwise. And that produces my binary image. So let's talk about what would be a good candidate for this halftone array. Okay? So let me give you one example. So here I'm going to use a 5 by 5 array for H, which means I would block up the original image in 5 by 5 blocks. And so I'm going to put some numbers in here, and at first they may seem kind of random, but then we're going to talk about why these numbers make some sense. So you'll notice that what I'm going to put in this array are basically the numbers from 10 to 250 in units of 10. Oops, 200, 220. And if you look carefully, you see there's a pattern here, right? So the idea is that, you know, here I have 10, 20, 30, 40, then I have 50, 60, 70, 80. So kind of what's happening is that the numbers are filling in kind of like in a spiral pattern almost, right? So I'm kind of, you know, building up to a big number in the middle, and then I'm winding down to small numbers at the edges, okay? And so how does this help us kind of turn an image into black and white dots? Well, let's think about what would happen if I had a you know, constant intensity block of 50. So what that would mean would be that I'm going to add 50 to all these numbers, and I'm going to threshold so that anything that's above 255 will get turned to white. And so in this case, not that many pixels are going to turn to white, right? So if I think about what my 5 by 5 block is going to look like, so basically very few pixels will pass the test, right? So this one will pass the test because it'll be above 255, it'll be 300, right? So this one will pass, and this one will pass, but then 200 is too low, right? So the only pixels that will be white are going to be the cross in the middle, and the effective result is going to be a block that looks like this. And this kind of matches our intuition of what I should get is kind of a low intensity block should be mostly black with just like a little white dot. On the other hand, if I have a constant intensity of some brighter value, so let's say we use 140 instead, so that means that I'm going to be, you know, well above the threshold for a lot of these pixels, right? So basically, I have to be at least, so everything that's above, let's think about this, everything that's above, sorry, I'm late at night and my mind is freezing. Everything that's above 110, right, will work, right? Because as soon as I hit 120, that would be above 250. So that means that anything lower than 110 stays black, anything above that stays white. So that means that these guys here will be black, and these guys here, and these here, and these here. Right, so kind of what I get is a white blob that gets a little bit bigger, right? So, in some sense, here I think about this as like 50, 50 over 255 is approximately, 20%, right? That means that only 20% of these are turned on. 140 over 255 is about, presumably, if I were to count, 1, 2, 3, 4. So here I have 11 pixels turned on, so it's probably like 60, 56%, something like that. So I'm more on than off, right? And so this is a good way to do it because I end up turning on approximately the percentage of pixels that corresponds to how bright the image is. And so I can show how this works in a Matlab function that I wrote. And so if I go back to here, I wrote a function called Halftone, I assume. Halftone. If I could spell it right, I would show it to you. Okay, so here I've just taken this block that I just told you about and put it in an array. I basically split the image up into repeating blocks of that size. I add the image to it, and then I threshold at 256, right? So again, pretty straightforward. So let's see what we get with my, let's start with the image that I had before where I have this diagonal line, right? So here, let's see what happens when I halftone this image. Why can I not spell today? Okay, so this is actually looking more promising, right? So if I were to zoom in on it, what I see is that in the darker region, I get splotches of white that get bigger and bigger. And as I move the image kind of up to the upper left, these blocks of white get larger, and eventually they become, blobs of white that are, only leaving isolated dots of black as I go up this way. And so as I zoom out, this is looking not that bad. And let's see what happened to our other image. So this is definitely better than the dithering I showed before. And I think that, unfortunately, you're going to see some artifacts on the screen that more or less come from, I would call them moire patterns, basically. So let me try and zoom in on a place where we don't have any moire patterns. So here, again, you can see that the image is made up of black and white dots, but if I zoom out, I'm trying to think of a good way to show you this that doesn't suffer on the computer. Well, unfortunately, it's kind of a Matlab thing in terms of the screen resolution. But here you can kind of see that you can make out details of the image that are pretty good. If I were to zoom in on this, you could probably read the writing that says super smashed if you kind of squint your eyes, right? So, not too bad. And this is actually getting closer to the way that newspapers and so on do it, right? It doesn't quite look exactly like what I showed you through the microscope, but it is related. And so, obviously, the success of this technique depends on a lot of factors, right? So, the perceptual quality depends on several things. Certainly, it depends on the size of this halftone matrix that I used. So if I'd used 8x8 or 4x4, it would have looked definitely different. A lot depends perceptually on the shape of the blob that you get when you construct the matrix. And I'm going to show you another example of a halftone screen that produces kind of qualitatively different looking dots in just a second. And also the angle that I use can change. And so, for example, I don't need to necessarily split the image up into regular rectangular blocks. I mean, one thing that I could do would be to say, suppose I were to block up the image diagonally instead. And of course, this is a kind of crappy diagonal, sorry about that. Of course, I can't actually, make these lines beautiful, so probably what I would have instead would be kind of a jaggedly jaggedy pixelated block like this, and I could tessellate the blocks with, or tessellate the image with this kind of different shaped halftone array. And that's actually closer to, you know, what happens in printing. So I could tessellate with, you know, non-square tiles. And here's a point where this is actually the way that color halftoning works. Right? So if you've looked at the comic strip, you see images that look like this, right? So what I'm doing is I'm depositing, you know, yellow, pink, or magenta, cyan, and black splotches of ink on a piece of paper. And here you can see the idea is that I take basically the cyan halftone screen is oriented at one angle, the magenta one is oriented at a different angle, the yellow one is up and down, and the black one is diagonal. And when I add these things up, I get, you know, if you squint, a mixture of colors where the dots that are there are all on kind of different angled grids so as not to make your eye think that they're too regular, right? And so kind of here's an example of the orientations of grids that are commonly used in color printing. And so, for example, I think that the one in the previous page, yellow was, you know, 0, black was 45, and the other ones were like at 15 and 75. And then the result is images that look like this, which are, you know, pretty much like what you would see in your comic book or comic strip in the Sunday paper, right? If anyone still reads the Sunday paper. So this is actually what you'd get if you squinted in at a newspaper. So, you know, what I just talked about was pretty close to the way that halftone printing works for kind of like physical printing. And again, if you looked at the, you know, if you look at my refrigerator picture, although I don't know if I still have it in my area here. So let's look again at what my printer is doing. If I zoom back in here. So here you can kind of see that this is like a diagonal dot halftone screen. I apologize for the jerkiness of that, but you kind of get the idea, right? So this is, you know, much like, e.g., newspaper and book printing. So I don't know why I put parentheses here, like that. However, you know, I think that probably most people who are watching this video are like way too young to remember what older operating systems were like. So I grew up in college with Windows 3.1, which had a very limited color palette. I think there were only 16 colors, right? And so you ended up seeing a lot of kind of the equivalent of dithering and halftoning to take, you know, you could store higher bit depth images, but you could only display them with 16 colors. And so the idea was, how did you do that? Well, you did kind of a similar idea to halftoning. And so the images that I'm used to from, you know, my college computer used a kind of a different halftone screen. So an alternate approach is something like this. So here is a 4x4 halftone screen. And again, this has some structure to it. Oops, 13, 5, 15, 7. Sorry about that. And I multiply these numbers by 16 to get up to making this range between 0 and 256. So the idea here is that this will maximize the distance between dots that get turned on, right? So for example, you know, first this dot goes on, then this one, 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 and so on. So kind of what you see instead is, you know, this maximizes the distance between dots that are on and off. So kind of what you kind of get is what I would call like a crosshatch kind of effect instead of a blob kind of effect. So kind of what do I mean by that? Well, let's take a look at my images again. So in my function, I also included this alternate thing, which is called actually I think this is called a Bayer dithering, so I called it Bayer here. And so if I were to take my diagonal image and supply it with Bayer instead, what I see is kind of a qualitatively different looking image. And it's qualitatively different in the sense that instead of kind of getting blobs, what I kind of see are these more checkerboardy, for lack of a better qualitative word, patterns. And so they look like, you know, small black or white X's that change in size as I go this way. And you definitely see some sort of like definite banding that shows you in what region do I get certain shapes of X's. So, you know, again, you're seeing some kind of like Poiré pattern here on the screen that just comes from this being subsampled. So it's kind of important to look at it at a reasonable scale. This is probably more accurate. So I remember seeing lots of things like this in Windows 3.1 days, except it was like a color version of this and not a binary version. And if I do the same thing with my other image, let's see what we get. So this is a little bit better. Let me zoom in on something where I avoid the pattern here. So again, looking at this, this looks kind of like old school video game sprites in some sense, right? The way that this guy's face is tiled with you know, little crosses of black and white. So again, if I zoom in, it's entirely black and white. This is an image. This is an area that's mostly gray, and so it looks like it's a little bit more black than white. But in general, you know, you see that things are not too bad, and different patterns give me a sense of the shades of gray. And if I were to, you know, if you were to squint, you can definitely read this text that says super, for example. So this is definitely, you know, not a bad alternative. But there's still one more thing that we can do to make these images look even better. Okay, part of the problem with these half-toning screens is that you really see this regularity that your eye picks up on, right? You see this grid of dots. And so what we like to do is to say, okay, well, you know, in black regions, I definitely think that in a dark region I should have, you know, a sparse set of white dots, but I don't want them to be so regular that my eye picks up on it, right? That looks kind of bad. And so what can we do instead? Can we kind of randomly scatter these dots in a way that is less perceptual to the eye? So the answer is yes, and that's a cool idea that's called error-diffusion dithering. And the idea here is that, you know, in my previous attempts, I was basically dealing with every block or every pixel entirely independently, which meant that, you know, I could be incurring a lot of errors when I incur, for example, a constant intensity block, and I code that with a certain binary pattern, right? Instead, what we do is get a pretty nice looking image. If we, you know, push the error incurred at a given pixel forward. To reduce the overall average error. And so here's the idea. So what we need is a kind of a pattern. And so here I'm going to use a simple 2x3 array where this is the pixel that I'm currently going to quantize. And then I'm going to take the error at that pixel and I'm going to distribute the error fractionally at these other nearby pixels that I haven't coded yet, right? So this is called Floyd-Steinberg dithering. So let me be a little more specific here. So here's the idea. I take the error that I got here, and I take 7/16 of that error, and I add it to this pixel. I take 5/16 and I add to this pixel, 3/16 and 1/16. So let me give you kind of a pseudocode. So along each row, kind of a for loop around the pixels in the row. I take the pixel that I'm at, xy, and I quantize it. For example, I threshold it at 128. Okay. In general, I could think about this as any sort of quantizer. This applies to any number of quantization levels. So I basically quantize it. In this case, this is like thresholding. So this is more general. Okay. Now I have an error at that pixel, which is the difference between my original value and what I've turned it into, which in this case is going to be either 0 or 255. And then I distribute that error forward into the next pixel. I take what I had before, and I add to it 7/16 of the error that I had here. And similarly, I kind of take the next row, and I add some more error here, and so on. So these are the 4 pixels that I distribute the error to, none of which have actually been coded up yet. So I'm really changing these pixels in the image. I'm changing their values. And then I end. And so the idea is I keep on doing this along the rows, and actually what really works better, I think, is instead of going along each row this way, I instead do like a serpentine pattern like this. This is probably a better way to actually follow the pixels. So it's kind of like a serpentine scanning. And so how does this work kind of in practice? Well, let's suppose that I have a block that is kind of all 64s. So I've got a constant area where all these pixels are 64, right? And now I'm going to decide what should I turn this pixel. Should I turn it black or should I turn it white? So right now this pixel is 64, which is below my threshold of 128, and so this would get turned into a 0, right? And my error would be 64, right? That's the difference between 64 and 0. So my error over 16 would be 4. And that means I'm going to turn this into 64 plus, what did I say? I said this would be 7/16, right? So it's going to be 64 plus 28. I'm going to get 5/16 here. I'm going to get 3/16 here, and I'm going to get 1/16 here. So my new, block is going to now turn into, this has been quantized already. Now I'm going to get 92, 76, 84, 68. Now I think what's going on here, and I say, oh, okay, so now this is still below my threshold of 128. So this again is going to get turned into 0. Now my error is going to be 92, bigger, right? My error over 16 is going to be something, 5.75, let's say. And that means that my new image is going to look like, 0 has been quantized, 0 has been quantized. Now I'm going to add, all my pixels, and I'm going to get, this is going to bump up to 101, 97, and so on. And so eventually, this number here is going to bump above 128 by the time I keep on going through this row. So eventually, this will go to above 128, and then this pixel will get quantized as white, right? So that means that most of the pixels in this constant 64 area will still be black, but occasionally one of these guys will get bumped up to white, and then the error will be negative, right? Because that means that I'll have extra error that now will bump these guys down. And so the idea is that, eventually the error accumulate and diffuse to bump, pixels above or below the threshold. And so let's see, what would happen with my image here. So actually, Matlab has a built-in function, they call it dither, to do exactly this, right? So if I look at this dither command, if you scroll down, it asks about what is the algorithm. It's exactly this Floyd-Steinberg algorithm that I just told you about. And so if I look at my diagonal image and I dither it with Floyd-Steinberg, now, this looks a lot better in some sense, because if I zoom in on an image, I can see that the distribution of white dots is exactly what I want. It's sparser down in the lower left, but it's not regular, right? There's no real regularity that your eye picks up on a lot. And as I push up into the other regions, this is definitely kind of, more half and half black and white, but there's no real patterns to the half and half that your eye picks up on. It almost looks kind of randomish. There's still some structure to it, but it doesn't look bad. And as I move up this way, the black dots become sparser until I get this. So, I mean, it's actually pretty good. And if I do that to my other image, well, this looks awful because of the moire pattern. So if I were to zoom in a little bit here, let me zoom in on like this region here. So here I think we can all agree that the image here looks a lot better, right? So in dark areas, I've got a few white dots. In bright areas, I've got a few black dots. Everywhere else, it's kind of like just about the right amount of black versus white without really looking like there's a pattern. Like in this kind of area that's kind of, maybe this could be like our 64 level area, we don't really see a pattern so much to the white dots. So I think this looks pretty good. And of course, you can do variations on this kind of Floyd-Steinberg dithering. Instead of using that smaller array, instead I could diffuse the error more broadly. So here's another possible array that uses 3 rows and 5 columns instead of 2 by 3. So if this is the pixel that I'm working on, then I could say I'm going to diffuse lots of error here, smaller amounts of error here, smaller amounts of error here, and here. And then I divide this by 42 because that's what these numbers add up to. This is called the Stucky dithering pattern. And so as I said, all this stuff is generally applicable to not just black and white, but any situation where you're reducing the color depth or reducing the bit depth of an image. So it's pretty cool. And the last thing I wanted to mention before I leave this topic is that, kind of off topic, let me say, because this isn't really image processing, it's more like computer graphics. I would say there are kind of cool computer graphics approaches to what I would call non-photorealistic rendering that are kind of relevant to this idea, right? So how would an artist render an image from a color or a grayscale photograph to black and white? They're probably not going to try to slavishly copy the grayscale level of each pixel. They're going to give you the gist of the image with a careful selection of black and white brushstrokes. And that's the way the artists, that's what they have, is they have a pen, right? So they're going to draw the contours of a person. Of course, you can tell that I'm no artist, right? But they're going to kind of want to draw something that mimics what they see without really being a grayscale reproduction of it, right? So for example, a good example of that, which I, unfortunately I don't think I had queued up here, but I guess I can look for one, is like, let's just Google, like the Wall Street Journal has these portraits, right? So here's a good example. These are grayscale images, or they're black and white images, but they are actually made up of kind of carefully selected dot stipples, right? So you can see that here, here this is kind of more like the dots that we looked at before. Here in his hair, there are more like wavy lines, and here there are lines along the suit jacket that kind of accentuate the suit. So here, this is something that is perhaps a combination of an artist and a automatic tool. So how does that work? Well, one idea is by thinking about how do artists draw strokes. And so here are some papers that are from actually quite a while ago. This is one I've always liked from SIGGRAPH 99, Viktor Ostromokov, on facial engraving. So here, this portrait on the dollar bill does look kind of similar to the Wall Street Journal photographs, right? So the idea is that we draw black contour lines along surfaces that we know to exist in 3D, right? And so the question is, can we get a computer algorithm that does the same thing? And so here, this author has thought about how engraving, like the way that bills are created by taking a metal plate and carving out trenches in the plate and filling that with ink and then pressing out a piece of paper. That's called copper plate, right? And so here, this is kind of like a computer simulation of copper plate. And it uses the knowledge, if possible, of the underlying 3D geometry to help decide what the orientations of the lines should be, right? So here's an example of carefully, so you've got a 3D model, and you can make the copper plate engraving lines kind of follow the contours of the 3D object. And if you don't have the 3D model, all you have is a photograph, for example, you can still kind of manually guide the algorithm to kind of draw some strokes and say, okay, the cheek is moving this way, this is hair, so that I can draw some contours of the hair. So some user guidance can help make this engraving process work. And here's kind of an example of doing the same thing in color, where along the face, you're doing some kind of color version of the engraving with different directions of lines to accentuate, different colors. And maybe in the background, you're doing something that's basically more like normal color dot halftoning. Another possibility is something, this is actually something that's a little bit more related to edge detection. So I've got an input image. Again, if I want to kind of have a stylistic version of this, the idea is to find the important edges and then use different line thicknesses to convey which edges are more or less important, right? So strong edges here, like between the black and yellow regions of the butterfly, are given a stronger line weight, and fainter edges are given a smaller line weight. So this is still a little bit synthetic looking, but I mean, this is a great example. Like this, I think this rendition of the eagle is pretty slick compared to the original thing. And this is not at all like dithering or halftoning. It's very different. I think some of these images look pretty good. I mean, some of them look kind of computer generated, but like this lighthouse image, for example, or this Pantheon, I think these look, kind of stylized in an interesting way. And finally, there were definitely some papers in the late 90s that were oriented towards thinking about how do people crosshatch, how do people, artists tend to crosshatch an image in order to make it seem to have kind of realistic depth, right? So here's an example of taking, again, here we have a 3D model again, but different strategies for pen and ink illustration. So the idea is all you have to work with is a black pen, and so here we're drawing lines automatically that follow the contour of this 3D model, and in non-contoured regions, we kind of stipple it in a similar way to error-diffusion dithering. Here we're doing something different to the shadow. And again, you can use different lighting will give you sparser or denser strokes along the surface of the object. And so again, some of these pictures look pretty good. Like I think this is a nice example of like this butter churn. Here I think that the 3D model is very important to getting a good looking image. And there's definitely some user guidance to say, what kind of artistic pen and ink do you want in different angles. But, this is a pretty neat idea. And here's an example, again, of something that kind of combines cross-hatching, stippling, and so on. So again, if you're interested in this kind of thing, the place to look is kind of SIGGRAPH Proceedings, the Big Computer Graphics Conference. And again, this was really popular kind of in the late 90s, which is where my references are from. But I think there are probably still many similar things going on today. And even some of that stuff may be built into tools like, Photoshop, for example, may have some of this stuff built in. Okay, so that was fun, and we'll talk a little bit more about things that are getting a little bit more off the beaten path, but I think that are interesting in image processing in the next few lectures. So see you next time.